Swayam Prabha. Digital India. Educated India.
So, we have been discussing creep, and then we have seen that the expected strength or expected creep resistance is of the order of a strain rate per 1000 hours to the extent of let us say less than 1% in 1 lakh hour, that is 100,000 hours. So, which boils down to 2.8 into 10 to the power minus 11 seconds inverse as a strain rate in creep. So, this is the kind of strain rate that is that can be tolerated. I mean that would be taken as a practically acceptable creep rate. In fact, the lower it is, the better it is. If it is 0, it is the best, but unfortunately if we cannot have it as 0, then we need to have it as low as possible, and therefore it should be at least less than 1% per 1 lakh hours or 100,000 hours. So, now the issue is that we need to find out how to resist creep, or how do we minimize this creep rate. Now, we need to therefore see the structural changes that take place during creep. So, one structural change would be that the dislocation slip or slip planes would change. So, the planes of easy slip will undergo a change. So, you can have a non-basal slip in case of magnesium and zinc, typically HCP structures, and in FCC structures you can have slip in these planes which will be activated above 200 degrees centigrade. We have seen that in crystal structures the close packed plane is the one that is a plane of easy slip. So, 111 plane in FCC is the plane of easy slip, but then planes which are not favorably packed, in the sense they are not closely packed, also will become amenable to slip above a certain temperature. So, so that is the reason why more and more slip systems come into play, and then the creep rate increases. So, one way to arrest creep is to make sure that the slip does not take place on these slip systems, and as the temperature increases, the critical resolved shear stress continues to decrease. That is one aspect. Second aspect is subgrain formation, and so we need to understand that formation of low angle boundaries due to easy climb and slip at increasing temperature leads to formation of subgrains. So, these are some of the structural changes during creep, due to which the creep becomes feasible, the deformation under high temperature becomes feasible. Add to that, you have grain boundary sliding taking place as the temperature rises. The interior of the crystal turns out to be stronger. In fact, it also softens, as we have seen there. It also softens because of dislocation slip becoming easier and subgrain formation becoming easier, but because the grain boundaries soften faster, you will find that the grain boundary sliding is something that starts taking place, due to which the strain in the grain tends to reduce slightly. Strain due to grain boundary sliding, and this strain has to be accommodated by the process of diffusion, which is fairly slow. So, grain boundary sliding is the active mechanism, and so as the temperature is large, strain rate is low, then you have grain boundary sliding as a predominant mechanism, and that is perfectly that perfectly fits in with the fact that when you have diffusion, which is a slow process, you need sufficient amount of time and sufficiently large temperature. So, we have these two things possible when you have high temperature and a lower strain rate, because you have more time available under these conditions. And then this grain boundary migration or the diffusion results in balancing of the material. For example, you do not have accumulation of material at one end and deficit on the other. So, these compensatory mechanisms continue to operate and balance the two. So, we have different viscosities in creep, and so we have seen that the thermal activation of the diffusion process follows the Arrhenius type law, and so strain rate is equal to A sigma exponential minus Q by RT, where Q stands for activation energy for diffusion. We have seen creep mechanisms in polymers and also steady state creep in crystalline materials, and we have seen that there are different mechanisms resulting in different values of these exponents of M and Q. Now, this diffusional creep is through the crystal. So, the crystal area is the one that is important. So, Q is 2, whereas diffusional creep is along the grain boundaries. So, vacancy diffusion along grain boundaries. So, the surface area of the grain comes into play, and that is proportional to the R cube, that is the cube of the grain radius. So, that is the reason why these exponents are different for Nabarro-Herring creep and Coble creep. For power law creep, there is dislocation activity. So, basically dislocations are the ones which are active, and therefore, this happens at relatively lower temperatures and relatively lower stresses. So, the dislocation glide takes place to climb, and after climbing over obstacles, the thermal part of the energy results in dislocation climb, and therefore, obstacles are avoided and dislocations continue to glide after climbing over the obstacle. So, this is how obstacles get circumvented and the creep strain continues unhindered. Harper-Dawn creep also we have seen, it is again due to dislocation climb, and so these are the different mechanisms of creep. And so, if one has to reduce creep, one can see that consistent with these with the mechanisms we have seen, it is important to reduce the grain boundary area. So, the coarse grain size is the best as far as creep goes, as well as we need to have some metallurgical features or metallurgical factors that will also prevent the dislocation movement if we have to control the power law creep. So, we have seen that when different creep mechanisms operate, they operate in different domains of temperature and strain rate. They operate in the different mechanisms of temperature and time that is available, and therefore, we see that at relatively lower temperatures we have no creep at all. You have elastic deformation, then there is a permanent deformation even when you are below the yield strength. So, all these stresses are below the yield strength, and in spite of that you have significant diffusion and diffusion related plastic deformation which is called as creep. So, now we see here different creep mechanisms based on the what is called as Wiertman-Ashby maps, and for different materials, for example, here we take silver, which is a face centered cubic, tungsten is a body centered cubic material, and we have different mechanisms of creep operating at different conditions. So, you have normalized tensile stress, and you have different homologous temperatures. So, homologous temperatures ranges from 0 to 1, and you have what is called as Coble creep at relatively low stresses, and you see that the Coble creep starts at relatively lower temperatures as well, and dislocation creep is also present even at relatively higher temperatures and relatively higher stresses. Now, here this creep is also grain size dependent. For instance, at grain size equal to 10 microns for a given homologous temperature, you would have creeps taking place at a relatively lower normalized stress as compared to a 32 mm, which requires a much higher normalized stress for the creep to take place, which means that as the grain size increases, the resistance to creep is increasing. So, that is the point being made here. And then you have at high temperatures, very high temperatures beyond 80 or 90% homologous temperature, a Nabarro-Herring creep. You have Nabarro-Herring creep in this region, and so that is a creep which involves diffusion of vacancies through the lattice, right. Okay. So, this is about silver. Now, silver has got very high diffusivity through the crystal lattice, that is because of the face centered cubic structure. For the body centered cubic structure, the situation is very different. If you look at this, then you see that the creep rate at, let us say, 0.6 seconds inverse is sorry 0.6 homologous temperature at so here, for example, you take the region of Cobalt creep, it is 10 to the power minus 10 per second, whereas it will be much higher for silver, and that is the reason why tungsten, which is body centered cubic, resists creep by virtue of an atom sitting at the center of the crystal lattice. So, that atom results in some blockage of diffusion. The ions or the atoms cannot move, very easily through the crystal lattice, and so diffusivity through the crystal lattice with tungsten is far lower than what you have for silver. Now, here in case of silver, you have the strain rate as 10 to the power minus 8 seconds inverse, 10 to the power minus 8 second inverse, and so you see here that, so this is the line corresponding to 10 to the power minus 8 seconds inverse. Grain size is 10 microns, which is over here. 0.6 is the homologous temperature, and at that the stress, corresponding stress is between 10 to the power close to 10 to the power minus 5, whereas in case of tungsten at homologous temperature of 0.6 and strain rate of 10 to the power minus 8 per second, you will have a relatively 10 to the power. So, this is sigma by G. G in case of tungsten is very high, and therefore, sigma by G is 10 to the power minus close to 10 to the power minus 7. So, even at that you have very high creep resistance, meaning lower rate of creep. Here dislocation creep is something that happens again like in case of silver, you have dislocation creep also here, and at 10 microns grain size, which is very fine grain size, the creep rate is the creep happens at a relatively lower stress. So, as you see here, 10 to the power minus close to 10 to the power minus 7 is the stress at which the creep takes place. So, this is Cobalt creep, and this is basically diffusion around the grain boundaries. So, the Cobalt creep would be proportional to cubic power, that is d cube, and so the grain size it is much more sensitive to grain size as compared to Nabarro-Herring creep. Nabarro-Herring creep is sensitive to the square power. So, that is the difference it makes. So, you have in Cobalt creep at 0.6 homologous temperature for the same 10 microns grain size, a much lower stress at which normalized tensile stress. So, the absolute value of the tensile stress may be higher than what you have in case of silver, but then the proportion is 10 to the power minus 7 or something like that. So, I mean, we should not compare this at face value, these normalized figures at face value, because the absolute value here is going to be much higher as compared to that in case of silver. Now, if you look at different creep mechanisms, we see that there is a dramatic change in the creep rate when the creep mechanism changes from power law to diffusional flow. So, initially you have, let us say, power law. So, this is illustrated in case of nickel, and so when the creep mechanism changes, the creep rate changes very sharply. So, grain size of so for the creep rates of at 10 MPa at 800 degrees centigrade, 10 to the power minus 6 for grain size of 0.1 millimeter, 10 to the power minus 5 for the grain size of 0.01 millimeter, and 10 to the power minus 2 for grain size of 0.001 millimeter. So, this is so as the grain size becomes finer and finer, the creep rate increases very significantly, as we see over here, and that happens because of the change in the mechanism. As the mechanism changes from dislocation creep to so power law creep to diffusion creep, the creep rates are bound to increase quite significantly. Now, creep fracture is the final outcome of the of excessive creep, and so this has to be avoided. Now, mind you, you are deforming the material below the yield point. The stress level is below the yield point, and the deformation is occurring purely through thermal effects and time being available. So, temperature and time and activation energy promote diffusion, and this results in plastic deformation in spite of the stress being below the yield point of the material at that temperature. So, we must understand that here there is no yielding that is taking place the way it takes place in uniaxial tension, but here the creep is taking place purely because of the time temperature dependent flow of material or physical displacement of material taking place by diffusion. So, at low to moderate temperatures, metals usually fail by transgranular failure, meaning so low and moderate temperatures means the usual plastic deformation type of situation. As we had seen earlier, you will have more or less a plastic deformation taking place at yield strength, and underneath that you have just the elastic deformation. So, that is where you would have relatively low at low and moderate temperatures, you will have granular fracture taking place, probably because of plastic deformation setting in and failure taking place. At high temperatures, you have intergranular fracture, that is because the grain boundaries are weaker, the grain boundary sliding takes place, and wherever the grain boundary sliding and the corresponding deficiency of the material at one end is not compensated by the transport of material through diffusion, then you generate discontinuities, you generate intergranular cavities, and these cavities subsequently grow, they coalesce and finally generate cracks around the grain boundary, and therefore you get intergranular failure at high temperatures. And irrespective of so particularly you take Herring-Navarro creep, you will get failure irrespective of the fact that the stress might be low, irrespective of the fact that the grain size could be small or big. The creep rate will be governed by the grain size, but the failure will always take place in an intergranular manner in case of a Herring-Navarro type of creep. So, The reasons why cavity formation takes place is because of selective weakening of the grain boundaries, because the temperature is well above the equicohesive temperature, and equicohesive temperature is the temperature at which the strength of the grain and strength of the grain boundary both become equal. So, initially the grain is relatively softer, meaning the grain boundaries are stronger at room temperature. So, the deformation takes place inside the grain. As the temperature increases, the grain boundaries become weaker and weaker, and as the grain boundaries become weaker, the deformation tends to get concentrated more in the grain boundaries, and therefore, the strain related activity inside the grain continuously diminishes, and that is the reason why there is a selective deformation or selective weakening of the grain boundaries due to impurity segregation also, because now the impurities would segregate to the grain boundaries because the diffusivity is high at those temperatures, and grain boundary is essentially a region of disorder where the impurities can fit in very easily, and they can diffuse through the grain boundary as well. So, you have impurity segregation. Now, one thing must be made clear here, that in case the material has got low melting point materials, for example, if the impurity segregates to the grain boundary and undergoes melting there, then you will find that the entire mass of polycrystalline material will get disintegrated. That is because these impurities at the grain boundaries in a molten condition will not be able to sustain the loads which are coming on the grains, and they will not be able to sustain the integrity of the polycrystalline mass of metal. So, that is the reason why many times materials tend to behave hot short, meaning they just crumble at high temperatures due to the impurity segregation, particularly the low melting point impurity segregation at the grain boundaries. So, if the melting of the grain boundary takes place before so lattice melting point is higher than that of the grain boundary, then the grain boundary weakening can result in this hot shortness as well. Interaction of grain boundary sliding with geometrical constraints is also important, in the sense that you have, see, geometrical constraints means the constraint of maintaining continuity. Now, if the grain boundary is sliding, then it has in a polycrystalline material has got resistances from the neighboring grains as well. That is because they also get affected, and so by virtue of diffusion, these the voids or vacancies that are created due to the grain boundary sliding have to be compensated. The lack of material has to be compensated by the diffusion processes. Then you have interaction of slip bands with a grain boundary. So, you have slip bands interacting with the grain boundary, and these slip bands would also therefore alter the shape of the or profile of the grain boundaries. Enhance grain boundary diffusion in combination with stress concentration at grain boundary. So, that is another thing where the grain boundary, the diffusivity of the grain boundary can increase in the presence of stress concentration. This stress concentration can come from the presence of, let us say, a scratch, a crack, or any potential inhomogeneity. It could be a significant change in cross section, and that results in increased grain boundary diffusion. And so, basically the structural changes take place at very rapid rates because of the changes in the grain boundary structure or grain boundary profile, the nature of the grain boundary. In one case, the grain boundary becomes weaker, and as long as the impurities do not melt, the grain boundary sliding will be that much more severe, and the diffusion has to accommodate that severe grain boundary sliding. And then you have nucleation and growth of cavities at high creep rates and constant stress. That is because these voids tend to grow in number as well as size, because now there is a big gap between the rate at which the voids are created and the rate at which diffusion can compensate for the material that is deficient. So, at high creep strain rates, the voids are created at a much greater rate, and the pace at which the diffusion of material takes place does not happen or does not keep pace with the rate at which these discontinuities are being created at the grain boundary, and that is what leads to rapid increase in the creep rate, which is characteristic of a tertiary creep. Tertiary creep, you have a sudden increase in the creep rate at a constant stress. So, if you consider making materials resistant to creep, then at increased temperature we should have low diffusivity, because diffusion controls the rate, and therefore we should reduce the diffusivity to the extent possible and increase the shear strength of the material. Now, close packed structures are generally more creep resistant due to lower diffusivity. Actually, close packed structures meaning not in the sense that like FCC versus BCC, because in FCC the diffusivity is much higher in spite of the atomic packing factor being higher than body centered cubic. So, this statement should not be seen as should not be seen in relation with the atomic packing factor. So, this does not correspond to a high atomic packing factor. So, they are generally speaking let us say copper, aluminum, silver, gold, these are all close packed structures, but then they have very high diffusivity. But on the other hand, body centered cubic materials which are refractory alloys, molybdenum, tantalum, may not be tantalum, I am not sure about tantalum, but molybdenum, tungsten. So, these are all materials which are creep resistant because of their body centered cubic structure. So, diffusivity is curtailed, and then you limit dislocation mobility by introducing what is called as solute drag, precipitates and dispersed particles, which will prevent the movement of dislocation. So, even at those high temperatures, these high temperature precipitates, the precipitates are the ones which will not get dissolved at high temperatures. So, basically these are precipitates like carbides of refractory materials, for example. This would prevent any kind of grain boundary movement, because they just do not get dissolved in the parent matrix even at high temperatures. Similarly, limiting the diffusivity, so you decrease the grain boundaries, that is the whole idea of grain coarsening, because we have seen that all diffusion based processes of creep are sensitive to grain boundary area. So, grain boundary area is an extremely important parameter to permit creep by grain boundary sliding in particular. So, both Nabarro herring and Koebel creep are sensitive or non-linearly proportional to the grain size, and therefore, if you see the lower is the grain size, higher is the creep rate for both these processes. So, if you limit the diffusivity by removing the grain boundaries or minimizing the grain boundary area, okay, then one can minimize the diffusion paths. So, the least you can do is have a single grain. You have one grain, and whatever grain boundary area it has is the minimum you can have. You can't reduce the grain boundary area below that. Plus, you have some solute elements which can also hinder diffusion. So, these are the various steps which can be taken to make the material creep resistant. So, the creep resistance is induced by not decreasing temperature. Temperature will always increase, because we have to make we have to consider that creep should not take place in spite of the temperature being high. So, that is what we mean by creep resistant materials. So, in spite of temperature being high, in spite of the driving force for diffusion is being high, we have to reduce diffusivity by metallurgical means, and those metallurgical means are like introducing solute drag or precipitates or dispersed particles. So, these are metallurgical means by which, in spite of increase in temperature, we will not have a high creep rate. and then as a strategic consideration we would have a single grain. Strengthening mechanisms effective only in the correct portion of the deformation mechanism map, that is dispersed particles would control power law creep only. They will not affect Nabarro, Herring and Coble creep. So, our precipitates and dispersed particles are the ones which will be operational or which will be effective in the power law creep or dislocation creep area, whereas once you have gone into the grain boundary diffusion based creep area, then when the mechanism of creep changes, then the creep rate will change dramatically, because the mechanisms which operated to resist creep are no longer operational. So, that is the reason why there is a dramatic change in the creep rate, as we saw earlier also, in response to a change in the mechanism of creep. When we take superalloys, these are the alloys which are meant to resist high temperatures, and therefore, they are supposed to not deform at high temperatures, and so these are typically alloys based on iron, cobalt, nickel, and so these are like superalloys. Inconel 718 is a very popular superalloy. So, Inconel 625, 718. So, these are alloys involving nickel, cobalt and iron, and these resist temperatures at and these alloys resist deformation at high temperatures. The service temperatures up to 1200 degrees centigrade are possible. So, now these materials also need resistance to oxygen or oxidation in addition to resistance to creep. So, these are some of the issues which have to be kept in mind when one chooses material for high temperature service. Not only the creep, not only resistance to the mechanisms of creep, but one has to resist oxidation also at high temperatures. So, lifetime has to be close to about 20,000 hours of actual operation. It is not 20,000 hours from the time you have installed the superalloy part in the equipment. These are 20,000 in service hours. So, when you talk about turbine blades, these are so the life of 20,000 hours is when the turbine blades are at the operating temperature, and they are subjected to the kind of pressures and loads characteristic of normal full load service. So, typically in nickel based superalloys there are about 10 constituent elements and 10 trace elements. Now, trace elements are the ones which are added or which are there, not necessarily added. So, trace elements would mean that either there are impurities which could not be removed, and therefore, the traces of impurities left remain behind, or certain elements which are added as trace to control the diffusion rates. So, the precipitates which form or the intermetallic particles that form could be aimed at reducing the grain, reducing the dislocation movement inside the grains. So, small cube shaped gamma dash particles coherent with the gamma FCC matrix. So, these are the ones which are present, and they are there to reduce the creep rate. Now, these precipitates again will be effective only when you have power law creep present in the material, because these gamma dash particles are shear resistant, and they are used to the highest homologous temperature of any alloy system, that is of the order of 0.9. These are often coated to limit environmental attack, because oxidation is a problem, as we have seen, and therefore, it is important to save the material from hot corrosion or even oxidation by coating them with environmental environment resistant coatings basically. So, refractory alloys are the ones which can be used, but again refractory alloys have got although they have got very high melting points, molybdenum, tantalum and tungsten. So, these alloys have oxidation resistance which is quite poor. For example, molybdenum forms different states of or different kinds of oxide, of which the third oxidation state, that is MO3 or something like of that kind, would is volatile and therefore it just evaporates. So, you have these, even tungsten gets oxidized, and the oxide of tungsten, that is WO3, that will also evaporate. So, these refractory alloys when oxidized have this weakness. So, they will no longer serve the purpose of imparting structural strength, and therefore, one needs to prevent their oxidation completely. I mean, these articles made out of these materials operating at high temperature have to be coated all over to prevent oxidation. The oxidation has to be scrupulously kept away from these materials. Otherwise, we will lose these materials very rapidly, and nothing will be left of that part in question. So, we have been discussing about turbine blades. So, we have different ways of making turbine blades, and you have a polycrystalline turbine blade which is shown over here, which is made by conventional casting. Here they have made this by what is called a directional solidification, due to which you have got columnar grains. So, the grain size is big, so it is much bigger than what you have over here, because it is just a polycrystalline blade which is made by conventional methods. So, this will not be high temperature resistant, whereas here that high temperature resistance will be, that is creep resistance will be significantly higher, because the grain area, the grain boundary area is much smaller than here, and even if the grains are larger, there is also directionality. The directional solidification has imparted directional properties to the turbine blade, and therefore we will have greater strength in the direction of applied loading. However, the best thing to do is a single crystal. So, you have a turbine blade made from a single crystal. So, what you do is you make a single crystal. It does not have to take the shape of the turbine blade right from the beginning. You develop a single crystal in the form of, let us say, parallel piped or whatever section you might be able to get, a slab maybe, and you can forge the single crystal to the shape of the turbine blade and subsequently coat it with the oxidation resistant materials. So, this turbine blade has got the best creep resistance. So, here the creep resistance is poor, here it is intermediate, and here this is the best. So, if you look at the creep resistance here, the creep strain percent is shown here. The conventionally cast material has within say 30-40 hours itself will have significantly higher creep strain, whereas for the same thing to develop with columnar grains, you will need something like 60 to 70 hours, and for monocrystal, single crystal, even beyond 100 hours it will last. So, the creep strain percent increases far too slow as compared to at high grain sizes, large grain sizes, or even monocrystal, as compared to a conventional cast condition. So, if one wants to make turbine blades creep resistant material by directional solidification, one needs to have molten material in the furnace, and you see that the form is slowly drawn out of the furnace into the coolant. So, slowly the form gets drawn into the coolant, and you have progressively directionally solidified material. So, here you see that this is the outer metal, and so here there is a coolant. So, cooling front proceeds from here towards the top, from bottom to the top. So, here the metal is maintained in the molten condition in the furnace, and below that you have the coolant. So, part of this form is the part of the form is in the coolant, part of it is in the furnace. So, as you slowly withdraw this part, you have solidification taking place on this surface, and the direction of growth of the grains will initially be in the direction of temperature gradient, and as you withdraw the form progressively the temperature gradient will be consistently set up in the vertical direction, and then you get columnar grains. So, fully solidified and oriented polycrystalline cast grains are obtained, but this is still not a single crystal. So, single crystal is something that you can do by having a seed crystal, and then using that you again put the seed crystal in a similar furnace, and then you draw the seed crystal out of the furnace at a very slow rate, so that the melt solidifies around that single crystal. Then it will take the same orientation of crystal lattice as the seed crystal, and then grow in that particular direction, and therefore you will have one single orientation of the entire crystal lattice. So, very long range order that will be produced by virtue of very slow drawing of the form, and this way you will get a continuous single crystal which can be forged to the shape of the turbine blade. So, this is another method of getting directional solidification by a specifically selected channel geometry, which is shown over here, which is called as the spiral pigtail. We will see this the details of this solidification mechanism and how it generates a single crystal when we discuss solidification structures, but then for now we can see it as a way of getting a single crystal turbine blade which is creep resistant. Our important consideration is creep resistance. Now, when we have creep resistant materials and we have to prevent them from oxidation, from environmental degradation, then it is important to apply coatings which will withstand those service temperatures, which will withstand those high temperatures. So, we need to therefore have let us say thermal barrier coatings which will generally result in relatively lower temperatures, the blades being maintained at low temperatures, and most importantly prevention of oxidation. So, both these purposes are achieved by applying thermal barrier coatings. So, if you look at this, if this is a maximum flame temperature, then the flame temperature which is below, which is inside the blade with cooling and thermal barrier coating is quite substantially reduced as compared to the temperature that would otherwise be present. Now, blade cooling is often done using what is called as micro channels which are produced inside the blade. So, turbine blades have micro channels through which the coolant fluid is made to flow and take away the heat from the turbine blade. So, lower is the temperature of the turbine blade, lesser is the propensity for oxidation, as well as higher is the strength of the turbine blade. So, if the temperature can be maintained lower by blade cooling, then the possibility of creep is that much reduced, because you see that as the temperature increases, the propensity to creep increases very rapidly. So, that is the reason why blade cooling is a very important factor. And then thermal barrier coatings are the ones which bring down the temperature to some extent. Again, they cannot be as effective as blade cooling, but yes, they do bring down the temperature by maybe a couple of 100 degrees, but that will not be again a very significant thing, because a higher effect is produced by blade cooling. So, that is the reason why it is important to have micro channels in these turbine blades. And you see the evolution of these technologies over a number of years, and so earlier people were using not exactly single crystal, but they were using investment cast or conventionally cast nickel alloys, and they were relying more on blade cooling to prevent creep, whereas subsequently these technologies were available, plus an additional factor of being able to control grain size came into play until 2010, and therefore the life of the turbine blades increased enormously. Now, we have always been talking about creep being undesirable, creep not being we have been talking about preventing creep or resisting creep all the time. In some places creep is desirable, particularly because in concrete, for instance, it relieves tensile stresses which might otherwise lead to cracking. So, if there is in case of concrete, the steel bars are supposed to take the tensile loading. The compressive loading is taken by the cement mortar mixture, and the tensile loading is taken by the steel bars. Now, these steel bars will be under tensile loading for years, and so they may be at room temperature or whatever temperature that might prevail over a period of time, but they are always under tension for years. Now, like any other material, the steel which is used as a reinforcement, that is bound to creep, and because of that creep, which is again not very significant at all, because that creep happens at extremely low temperature. So, the creep rate is going to be extremely small, but that performs the vital objective of that perform the vital function of preventing cracking. If the creep had not taken place, there was a great risk that the stresses prevalent for a very long period of time can lead to cracking of the steel bars, but that does not happen only because creep is possible. Then you have extrusion, hot rolling, hot pressing. So, in fact, many manufacturing processes are based on creep. So, they are very slow processes, and creep forming is a process where you use creep mechanisms for changing the shape of the material and achieving the final shape. So, basically creep is desirable where your objective is to use creep as a mechanism of deformation. You want to use creep to, let us say, relieve stresses or reduce stresses in the material. So, basically you would benefit from creep when you want when you bring it out of intention. Normally you would always prevent creep. It will still remain. I mean, it is not that creep can be prevented completely, but you would minimize the creep so that the structural integrity, the geometry based on which the component is operating, so that geometry has to be preserved, and only a low creep rate, resistance to creep, is going to be important to achieve that. So, let us take a problem now pertaining to a pressure vessel which works at 950 degrees centigrade at a constant internal pressure of 40 MPa. So, this kind of case study, and in this problem it is basically a problem of designing the thickness of the pressure vessel using two different criteria, and we will see how how insufficient the criteria pertaining to yield limited design and fracture based design would be when it comes to preventing failure by creep. So, let us go through this problem and then come to the issue of creep. So, pressure vessel works at 950 degrees centigrade at a constant pressure of internal pressure of 40 MPa. The pressure vessel is 1000 millimeters in internal radius and is made from a steel plate which is 85 millimeters thick. The plate material has a yield strength of 860 MPa at room temperature, and this strength diminishes with increasing temperature at the rate of 0.39 MPa per degree centigrade increase in temperature. Check if the plate thickness of 85 millimeters is adequate. So, the plate thickness will be changed to a thickness that you suggest. So, if you feel that plate thickness is not enough, it will have to be changed to that plate thickness. The fracture toughness of the material was found to be 250 MPa per MPa meter raised to half at the working temperature, and factor of safety was taken as 2, and calculate the size of the internal flaw with and without factor of safety, and after fabrication using the plate of desired thickness the pressure vessel is to be inspected. So, basically we have to also comment about leak before break, that will be achieved or not. So, here we is the solution to the problem. 40 MPa is the stress. Well, the circumferential stress is based on PR by T as a formula. So, P into R divided by T. So, it is about 470 MPa or so. The yield strength is 800. Now, this has been calculated not taking the thickness into account. I think this has been taken based on purely the internal radius, I guess, and so we get 470 MPa as the stress. Now, the yield strength is 497.3 MPa based on the fact that it is 860 MPa at room temperature and it degrades at a constant rate of 0.39 MPa per 100 degrees centigrade. So, you have therefore 0.39 MPa I think per degree centigrade actually. So, just a minute, here it per degree increase in temperature at the rate of 0.39 MPa per degrees increase in temperature. So, every 100 degrees centigrade it will change by 390 MPa. So, you have this yield strength at 497.3 MPa, which is very close to the circumferential stress. So, naturally you need a factor of safety of at least 2. So, then that makes it so if you look at the critical flaw size here, it is about 80 MPa. So, what it means is that the plate thickness that is needed for a leak before break phenomenon to be achieved is of the order of 160 millimeters. That is because for leak before break the critical flaw size A critical should be greater than the thickness. Okay. So, this is a critical flaw size. Now, here A critical is 80.444. Since it is an internal flaw, the flaw size is taken as 2A and therefore, it is 160.892 millimeters. And so, for this flaw A critical to be greater than the plate thickness, the maximum plate thickness we can say is about 160 millimeters, and the corresponding stress on the structure is therefore 270 MPa, which is much less than 497.3 MPa as the yield strength of the material. So, basically one would be happy that at 270 MPa the material is not going to yield, and it also shows that the flaw size with 160 MPa plate thickness, the critical flaw size is slightly greater than the plate thickness. Now, if we take a factor of safety of 2, what happens is the critical flaw size is this much. So, our 161 or even higher thickness is okay if you take a factor of safety of 2. So, the stress of 270 MPa is okay for yield limited design, but now if you look at the creep properties, we have creep properties of boiler grade steel. You see that the chemical composition is this. So, this is called as a T91 tube steel, or basically boiler grade steel. So, chromium is 9%, molybdenum is 0.92, and some amount of manganese, and the other elements are meant for grain size control, or basically carbide formation, and for precipitation of carbides in general. So, at 923 degrees centigrade, for example, if you look at the creep rate, then at 75 MPa the creep rate increases within a short period of time. It is less than 10,000 hours. So, it is half of, so this is a logarithmic scale, 10 20, okay. So, let us say 5,000 hours, at immediately after 5,000 hours it will rapidly rise. So, creep rate will rapidly rise, or creep strain will rapidly rise in about 5,000 hours. So, the life is the smallest with 75 MPa. Now, if you take the situation at the 270 MPa stress that we are talking about, then the life is going to be even shorter. And now, boiler is an item that has to go on for years together. So, once you have a boiler running, it has to go on for years together. So, so that is the reason why this design, although it is okay for yield, it is not okay from the creep point of view. So, we need to consider creep as a and creep strain as a criterion for failure, and increase the thickness further to minimize the stress, or bring the stress to below, let us say 55 MPa or so. Now, 55 MPa is a ridiculously low stress for a material that will yield at something like 860 MPa at room temperature, but yes, it has to be that low in order to prevent significant amount of creep. So, if you take the stress, if you take 75 MPa, 175 MPa as the stress, the minimum creep rate is very significant, as you see here. So, I think therefore, as the creep rate increases, the rupture life comes down very significantly, and that becomes a limitation as far as the design of the boiler is concerned. So, we need to therefore increase the thickness further and make it resistant to creep. So, this is what I wanted to emphasize. Thank you very much.